Hi, this is Kurt Munson from HBM Prenscia. We're going to talk today about reliability test design, how to link fatigue and reliability over the next 40 minutes or so. Agenda today is really threefold. We're going to look at a couple things, and then we're going to look at how we can implement these concepts in software. First off, we're going to look at how we create durability test specifications. We may have parts that we need to run validation tests on. And the common question for a validation or a physical durability test is, how should we load it? What type of cyclic behavior? How should we attempt to damage this part? And for how long? In other words, how do we replicate the service loading that this part will see in the customer's hands? ENCODE has had a number of tools over the years to help us with this, looking at fatigue damage equivalents and such. And then we're going to expand upon that, agenda item number 2, which is how do we introduce reliability into the equation here. So maybe we need to not just demonstrate that our A part will pass this test, but rather there's some distribution or characteristic of a distribution that we need to prove. For example, we need to show reliability of 90% or reliability and confidence of some levels. And that will require us to understand a little bit about the Weibull distribution or life data analysis and life distributions in general. We also need to review what do we mean by reliability and what is this confidence level as well. The reason why we talk about these things is that will help us understand critical components of our test specification, like how many samples should we test and how long should we test for? And maybe is there some link between those two? If the number of test samples that we have available to test is small, then maybe we can test longer. We'll look at that critical relationship. And then thirdly, we'll look at how we apply these concepts inside Reliasoft's Weibull++ tool. So we'll start with some PowerPoint today and end with a live software demonstration. Before we go too far down the conceptual and tool route, I want to talk first about Princey Access. So Prenscia is our software brand that incorporates both Reliasoft tools for reliability analysis and ENCODE tools for durability and vibration analysis. The intersection of these two is a licensing model that we call Princey Access that many of you have access to. The beauty of having access to Princey Access is that we can use a number of different software tools. As a matter of fact, the whole suite of tools that Prenscia provides for customers such as yourselves can then be accessed, allowing the use of reliability and DOE and vibration and fatigue and so on, test data processing tools, all in one common licensing app called Princey Access. I bring this up because we often talk in these webinars about reliability tools and reliability challenges or durability challenges and solutions to those. And today we're linking the two, and that's the beauty of this Princey Access licensing model in that it allows us to access both reliability and durability software tools. Now let's talk first a little bit about laboratory durability tests. So many of you guys are involved in this, and I hope you guys have had the chance to see some of these laboratory durability tests run. On the left we have an aircraft, and on the right we have some critical part of that aircraft. Maybe it's part of the body structure or something like that. And we've chosen to test that body structural component as we see on the right. So we've taken part of the airframe out, and it's being loaded with a single axis servo hydraulic actuator in this point. And the reason why we've done this is that we can test in a controlled laboratory environment and use this to validate the part for production without having to put it into actual customer service and risk early failures that way. So these validation tests are used frequently to understand production or to prove the durability under production circumstances. Now the challenge is that we need to correlate the loading in the lab to the loading that the part sees in the field. If we don't have correlatable loading, then the challenge will be if the part fails, for example, at almost a complete test cycle, let's say 80% of life. What does that mean in terms of customers' hands? Is this a problem that's going to come up quickly, or is this something we have time to fix, and what's the risk in doing so? So we want to have something correlatable service loading, and that may be correlatable in terms of magnitudes of loading, like we may not want to overload the parts in the lab. We may want to cap the loading that we see in the lab at levels that are seen in the field so we don't risk changing damage mechanisms or failure modes. We may use fatigue damage concepts of equivalent damage or equivalent fatigue tests. So for example, the service loading we see on the left here, the red measured time series data, that might be load or acceleration or strain or stress or something. We could calculate how much fatigue damage accumulates in the service environment. We've called that damage from service here. And then we can create a lab test spec that produces equivalent damage. So this uses some ENCODE tools, for example, to look at fatigue damage accumulation rates based on physics of failure and material data and so on. So the beauty of this is that we can tie together hours of testing in the lab with hours or miles or flights and so on of usage in the customer's environment thanks to this damage correlation. And ENCODE's got a number of tools to help us with this. Now, if we focus solely on fatigue damage, the challenge is that we might get mistaken and end up with a test that just proves durability but ignores reliability. And what I mean by that is, if the world around us were deterministic, we would take one test article and subject it to equivalent damage loading, and if it lived, then we'd say all of them will live, a whole entire population will live. The challenge is, as we'll see later when we look at the probabilistic side of things, the challenge is that that's not realistic. We have variability not just in loading in the customer's hands, but also in manufacture, and also in material strength, and so on. So ultimately, we need to tie together durability and reliability. And the way we do that is by testing not just one sample for one life. Maybe we test multiple samples for longer times, or a few samples for a much longer time, and we use that to infer characteristics of life for the population. And that allows us to meet say, warranty targets and life and reliability and so on, those metrics. So these types of tests that we build, these durability tests we build in the lab environment can take many shapes. At the top, we see a very simple, what we call constant amplitude test, and this is usually used for uniaxial loading scenarios and where dynamics is not important. The idea is that we push back and forth and back and forth, and we're imparting a fatigue cycle over and over, this repetitive fatigue cycling to induce or to incur or accumulate fatigue damage in the device on test in the lab. And we can use equivalent fatigue damage rules to figure things out like how big should this test cycle be? How hard should we push and pull? And also, how long should we do it for? So the critical metric in defining this test spectrum is how many cycles of what size. And of course, we have a sliding scale, and then if we run larger cycles, then the number of cycles to failure is reduced for equivalent fatigue damage, which is just the same as saying, if I spend money on bigger things like fancier cars, I don't need to buy as many cars before I'm in serious financial trouble and may end up even being broke. We'll look at an example of this constant amplitude cycling test specification in just a second. The second set down block cycle is like constant amplitude, but a little bit more complicated. This is still a cyclic test, but now we've got multiple size cycles. In my graph here, this plot shows we have two cycles, a small one and a large one. Now, realistically, we know that when a part is being used in the service environment, it sees a full spectrum, a broad range of fatigue cycles. Think about this as you, say, drive to work. You might hit small bumps frequently and some moderate bumps, and maybe, unfortunately, every once in a while you hit some big bumps. And we have some kind of a spectrum, probably, of a lot of them small and some moderate and hopefully just a few really large ones. This concept of the block cycle test hopes to better replicate that spectrum of cyclic behavior that our actual part will see in the customer's hands by reproducing, say, small and large cycles, or small and large and medium, or sometimes we even see these block cycle programs may even grow to, say, 8 or 10 different blocks. And of course, the more of these different cyclic sizes we specify, the better chance we have of replicating the small, medium, large, that whole spectrum of cycles that our part will see in the customer's hands. Again, this is usually done in conditions when dynamics are not important, and also where loads are uniaxial. Now, multi-axial loads and dynamics, if we move down further, we have this time domain specification. Sometimes these are done as what we call MTS or RPC-controlled tests, where time waveforms can be reproduced on the test rig. These test rigs can get quite expensive, but the beauty of them is that they can reproduce time waveforms, which means we can have multi-axial loading. It also means we can reproduce dynamics. So if we have excitation leading to dynamic stresses through resonance or other conditions like that, then this type of test can reproduce that for us. That's a good thing. So we call this a time domain waveform or RPC controlled test. And lastly, at the bottom is a test specification where dynamics are critical, absolutely crucial. And this is a test specification called a frequency domain or electrodynamic shaker testing, or sometimes this is called PSD random loading or sine sweep loading, where we're specifying the excitation that the part will see based on a frequency domain approach. So this is a PSD of loading you see in the lowest picture here. So this says here's the excitation energy as a function of frequency. And one further step to this that we would need is how long to run for. So not just what cycles and how long to run for, but rather what frequencies, what magnitudes of those frequencies, and how long to run for. This is often used for smaller parts that are inertially loaded because in this type of test with an electrodynamic shaker, the part is going to, the stresses are going to build up in our device on test solely because it's fighting against its own inertia. Now, ENCODE has tools to help with all four of these types of test specifications based on fatigue damage equivalents and frequency spectra and fatigue damage spectrum and all kinds of neat things like that. And if you look on our archived webinars, you'll find on encode.com, you'll see we have webinars that talk about these other use cases in more detail. We're not going to dig into too much more detail about these right now. Just suffice to say that there are a number of different ways we may excite the device in the test lab. We may excite this part we're testing, and we need to decide up front whether dynamics are important and so on, and choose the appropriate route, and ENCODE tools can then help us define that test specification. Here's an example of a test specification. This is some measured loading on a loader arm. So let's say we're working with a piece of construction equipment, and the load on the loader arm causes stresses, and those stresses may cycle, and those cycling stresses may lead to fatigue damage problems and, say, cracking welds and breaking structural elements and such. So the measured loading is up in the upper left corner, and we want to reproduce that measured load in some way on our test rig. Now, we could do this a number of ways using a RPC controller directly in the time domain. In our case here, we've decided, let's just say, that our loader arm behaves quasi-statically, no dynamics to worry about. And we want to run a test that's cheap and fast, so we're going to use a constant amplitude test. And what we've got down in the lower left corner is a function generator that's building up a sine wave. So we're replicating a simple constant amplitude cyclic test where we're going to have an actuator that's going to push, pull, push, pull, push, pull against that arm. And if we push and pull an appropriate amount for an appropriate number of cycles, in other words, load magnitude we need to think about, and also number of cycles we need to think about. If we get that right, then we should be able to replicate the complicated field service loadings fatigue damage accumulation we see in the upper left with a simplified waveform on our test stand. Then we can essentially, ultimately what we're after here is specifying how many cycles of what size will we have for an equivalent life in our test stand. And this process, this is actually a worked example in your ENCODE installation if you want to go play with this some. We're not going to dig into it in detail right now based on time, but this is worked example number 21 in your GlyphWorks worked examples, and you can explore this a bit on your own. The key thing out of this, key result out of this is the box we see on the right, which says that if we have a cyclic load of plus or minus 850 pounds, it causes some amount of fatigue damage per cycle. If we have the full variable amplitude measured loading history from the service environment that we saw in the upper left, it causes some, you can imagine, much larger amount of fatigue damage. And the ratio of those two is some quantity we can calculate using fatigue damage rules. If we go through those calculations, we find out then that fatigue damage equivalence says that we need 50,000 cycles of plus or minus 850 pounds to be the equivalent of 4,000 service hours. Now, what is 4,000 service hours? Let's just say that our loader arm on our construction equipment here is being designed with a target life of 4,000 hours. In other words, this fatigue test needs to replicate the fatigue damage equivalence of 4,000 service hours, and the cycle that I've chosen, plus or minus 850 pounds, can do so in 50,000 cycles. Now, you can imagine that's kind of a sliding scale here, that if I were to increase the load magnitude, the number of cycles required for equivalent damage would decrease. And likewise, the number of cycles required for equivalence would increase if I were to decrease the load magnitude. Now, there are a lot of rules we need to think about in terms of to what extent can we increase the size of the cyclic load. We have to be careful with this. We don't want to increase the cyclic load too much, maybe no higher than some of the larger load cycles we're seeing in the field, because we don't want to either shift failure mechanisms, or we may have limitations from the test rig. We can't produce loads higher than something because of the test rig actuators we're working with, and so on. So point is, there's some things we got to think about, but if we think hard enough about this and use some analytical tools like we see here, we can quantify how many cycles of what size for fatigue damage equivalence. Okay, so this is good. Now, the question still remains, how does reliability tie into this? Or, to put it a different way, if my requirement is to specify that not just one part passes, but I need to understand the reliability of the population, say a specification may be 90% of parts must pass one life. Oh, and also we have some confidence interval that we need to think about as well. How does that come into play? What about this reliability and confidence? So, you know, this is great. Our test specification may say the part must be free of visible cracks after 4,000 hours of representative loading. But here's the challenge. What about that 90% reliability and 90% confidence? Now, I'm not saying 90% is some magic number. Your life target or your company's goal for reliability may be something different than this. It may be we want to demonstrate a mean time between failures, MTBF, of some number. Or we may want to demonstrate that the reliability is greater than 95% with a 90% confidence level. Or if a really safety-critical part and we're worried about risk, and you know, we may end up saying we want to look at a 99% survival rate. So anyway, the question is, what do we do with that then? What do we do with that 90% reliability and 90% confidence requirement in this particular loader arm specification? So that requires us to think a little bit about statistics. And this may be something interesting to you. It may be something you just kind of have to deal with. It may be something you have a background in. But let me try to describe as best I can where statistics is going to fit into this. We've always talked about fatigue. If fatigue is deterministic, then we need to think about how strong is the material and what's the geometry or what's the structural response like when our part is then given a load that we see in the upper right corner. So we have the load, we have the structure, as you know, the geometry is the plate thickness is nominal and so on. We have the material strength in the upper left, and then we can pull all that into a fatigue or durability analysis, and we may find that we're predicting that if those conditions were met, we had nominal geometry and nominal strength and nominal loading, that we end up with a nominal life. And that's all well and good. That gives us ideas about the maybe central tendency of life, but realistically, we know there's actually a probabilistic side of this we need to think about. There's actually a PDF or probability density function that probably describes material strength. Not every part that's produced out of a certain material will have the same characteristic strength. Likewise, in geometry, you know, every print that we produce says that the nominal thickness of this part or the nominal dimension is this, with some tolerance. So we have some tolerances, and it may be that those tolerances work out to maybe reduce the structure's ability to resist load. So we have to think about geometry as a statistically varying parameter, and likewise with loads as well. Anyone that's driven with a teenager knows that variability of loading can be significant. I know for a fact that in my family, my kids drive differently than I do, and anyone that builds a car and doesn't recognize that is at risk of producing parts that may not last as long as they intend to. So realistically, variability in material strength, in part geometry, and in loads that the part sees are all going to lead to a probability distribution of times to failure. In other words, some parts will fail early, and some parts will fail late. And this becomes very important for us when we start to think about how do we prove or how do we demonstrate characteristic life values, like our specification just a minute ago said, we need to show that 90% reliability and 90% confidence that parts will be free of cracks. 90% of parts won't have cracks in them. We have to be confident in that as well after 4,000 service hours. So this is some statistical background. Now we got to think about how do we tie these statistics into the way we define our durability test. So what we're going to look at is we need to characterize the distributions of these inputs. So the probability density function can take different shapes. A lot of us may think about a varying parameter, maybe like how tall people are in the world. Maybe we might just assume that that follows a normal distribution. Why normal? That's because something we learned probably in high school, or maybe even grade school. We talked about the mean, maybe the average, we called it back then, the standard deviation. So there are lots of different models or functions we can use, like the normal distribution or the log normal distribution, which is says that the statistically varying parameter, like the load levels or the geometric thicknesses or the material strength, the log of their properties varies according to normal distribution. Or a Weibull distribution is used really frequently because it does a good job of recognizing that some failure modes are more likely to occur as time goes by. And fatigue is a good example of that, where as time goes by, we have a greater probability of failure. In other words, things wear out. Exponential distribution, the last one we see here, is not used much in durability because exponential distributions say that we have a constant failure rate over time. In other words, things just fail on their own without time influencing them in any way. Some people talk about this as car accidents or lightning strikes. And if we're designing against randomly occurring events, that might be useful. But in a fatigue and durability sense, we more often use a log normal or a Weibull distribution because both of them show increasing failure probability over time. So characterizing all these inputs becomes very important, right? You know, if something were to vary statistically, to get our arms around it, what we really need to do is characterize its distribution, not just its shape, but also its width and its height and such. And once we do that, we can start to think about things statistically. And that will help us with this reliability demonstration testing. So here's some probability distributions. We're going to look at some Weibull plots here. This is a Weibull plot in the bottom. If you want more detail on this, we'll have to look at, say, reliawiki.org or reliasoft.tv would be good places to go, because we're going to run out of time before we talk about every detail about the Weibull plot. What this is the y-axis is the probability of failure, and the x-axis is how long until that occurs. So the number of cycles, the number of hours, the number of flights, the number of miles, something like that. So this is on what some people call probability paper. This is percent of failure on the y-axis and amount of time on the x-axis. And if we have known failure data, we can do this curve fitting or life data characterization exercise and find out that our life distribution follows some characteristics. Like here's this Weibull distribution with a beta or slope of 1, and here's another Weibull plot, different distribution, a different set of failures, and now this has what we call a beta of 2. So that Weibull slope beta is kind of a measure of scatter. It's literally a slope, or what's called a shape parameter in this life distribution. What it really means is the higher the beta, the more closely grouped the failure times are, the more likely things are to fail kind of around the same time. And lower beta means that we have greater variability in our times to failure. So this is important because we can use this to try to help understand how do we build a test specification to demonstrate reliability. So remember this number beta. We'll see this inside our ReliaSoft demonstration in just a minute. And but before we dig into the software, I want to have you think a little bit about where does this distribution characteristic actually come into play. So let's go back to our question of how do we demonstrate our part being free of cracks after 4,000 service hours equivalents of loading, but we have to demonstrate also reliability of 90% and a confidence of 90%. So how do we do this then? So, one thing we could do is we could say, let's test a lot of samples. So we know what the cyclic loading should be on our loader arm when we put it on this, put it on some kind of a test apparatus. We looked at, I think it was 50,000 cycles at plus or minus 850 pounds to be the equivalent of some customer usage scenario. Now, if we want to prove that 90% of the parts survive, if we didn't know anything about statistics, or we knew just a very small amount about statistics, we might say, hey, you know what? Let's test 100 parts. Let's test 100 parts for one life, and if 90 of them live, if only 10 of them fail, then easy math, 90 out of 100, hey, that's 90%. 90% of parts lived after one life. That's cool. That's one thing we could do. The downside of that, of course, is the cost and the time penalty for testing 100 parts. Now, if you're making light bulbs, maybe 100 parts isn't so bad. But actually, more engineered structural kinds of things, that gets to be very onerous. As a matter of fact, sometimes it's hard to even go off and get the program people to agree to give you even more than a few samples. So that raises the question, can we test less samples? Or statistically, not just can we, but statistically, what method should we use to decide if we were to test less samples? How can we account for that? How can we make up for that? And also, how can we be confident in the results? Mathematicians talk about confidence as what percent of the time is our little group that we test going to be like the entire population? And the more samples we test, the greater confidence we have in that our test results really mirror the entire population, all the parts that we're going to produce someday, and the customer is going to go, unfortunately, go off and beat on. So how can we bring confidence into this? And how about this? Can we test for less than one life? Or conversely, what's the benefit if we test for more than one life? Could we use less samples and test longer? So statistical methods tie all this together. We can use statistics to our advantage. And the beauty of this is that these statistical tools are built into Reliasoft's Weibull++ software inside the Reliability Demonstration Testing tool, which we'll see in just a minute. Here's what the interface actually looks like. And rather than talking about what it looks like, we'll actually just go look at it live. That's going to be easier. A couple points before we go there, though. One is that confidence levels, sample size, and test time are all proportionally related. So, for example, if we want to have high confidence, we either need to test longer or test more samples. Okay, I don't think anyone will argue with that. Now, unfortunately, someone will argue with you when you say we need to have 10 samples to test, or we need to have 5 samples to test, or we need to run the test twice as long, because all those things are related to program cost and timing. But in general, the idea of we can gain confidence that our testing replicates the statistics or failure characteristics of the entire population by either testing longer or testing more samples. So clearly, we can reduce the number of samples by testing longer. So we have kind of a teeter-totter effect here, where more samples, less time, less samples, more time, vice versa. An important characteristic, though, is we're going to need to know that Weibull slope beta if we're shifting test time. In other words, if we say that we can't test a lot of samples, therefore let's test the subset, the smaller set that we have. Let's test them, say, for 2 lives. And if we try to project back to higher reliability at 1 life, that Weibull slope beta becomes very, very important. So to allow us to look at that teeter-totter effect of testing longer with less samples, you could say kind of the leverage point in that teeter-totter is built around that Weibull slope parameter beta. So let's go take a look at how this actually works. So I'm going to jump out of PowerPoint here, and we're going to go over here and look at Weibull. So this is Reliasoft's Weibull++ tool, and there's a lot of detail we could get into here, but this is not, today's webinar is not about how does Weibull work. Rather, it's how do we use it for one particular application, which is trying to demonstrate reliability in a durability test. So I'm using this life data analysis tool here. Let's just say on our loader arm that we have the previous generation. We had some information back from either from our test lab or from our proving ground or from our customers, and that helps us understand when did the previous generation loader arms fail. So what I've got here is a record of how many parts failed and at what time. Okay, you can see, I think we said we were designing our loader arm to last like 4,000 hours. You can see why we're redesigning this loader arm, because not one sample of the previous generation lasted 4,000 hours. Okay, you may be wondering, if we're redesigning something, why are we messing around with the previous generation? And the answer is, we're going to use the previous generation's life distribution to give us that key Weibull beta parameter, so we can look at how should we design the test for our new loader arm. So here's the failure data. And I can go off and run some analysis here like this. So this is doing what we call a two-parameter Weibull analysis. We have other life distributions we can use as well. And this says we have a beta slope of 3.15 and an eta, or characteristic life value. That's when reliability of 37% of the population still alive. That's 1,800 hours. If I look at a plot here, here's my Weibull plot. We talked about this a little bit earlier. This is unreliability here as a function of time. And here are my failed parts. So that's what I've learned about the previous generation. Now, the previous generation's over with. We're not building that anymore. We decided it didn't last long enough. That ship has sailed. So the reason why we're doing this is not to try to understand if the previous generation product lasts long enough. We know it doesn't. We have serious warranty problems with this. That's why we're redesigning. But the important thing is that from this life data analysis, we get this key parameter here, beta. So let's just remember that number, 3.15. We're going to use that in just a minute. And now we're going to think about how we plan our reliability demonstration test. So we may have, just as a reminder, let's go back here to what we did in ENCODE. This right here. So here we would go off and do some analysis in ENCODE, and again, this is beyond the scope of class today, but we could use these fatigue damage equivalence tools to look at an equivalent damage fatigue specification, which we see over here on the right side. So if you look in our recorded webinars, you'll see webinars on equivalent damage cyclic tests. And as a matter of fact, it even looks at this particular example. So in the interest of time, we're just going to say some analysis was done in ENCODE to come up with an equivalent damage test cycle, 50,000 cycles, plus or minus 4,000, plus or minus 850, excuse me, 850 pounds equals 4,000 service hours. So now, how many samples to test and how long? That's the big question. So we go over here and right-click, and I'm going to add a test design folio because I want to look at that whole question of test duration, number of samples, reliability, confidence, all that kind of stuff. So here's this Weibull slope parameter. So I'll type in my 3.15 here. And let's say we're going to run one life. Okay, so we're going to run one life, and we have a reliability of 90%. Let's just say our specification is 90% reliability with 90% confidence at one life. We said one life was, I think, 50,000 cycles, something like that. Now, this says, let's calculate here what's the required sample size if I run for one life. In other words, to prove R90, C90, by running one life, how many samples do I need? Run this, and it says, 22 samples. That may be a familiar number for you if you've looked at some statistics previously. So to learn about how a reliability of 90% with a confidence of 90%, we have to test a lot of parts if we're only going to test to one life. So, you know, usually if you go off and talk to the either the prototype fab shop or the program managers or anyone related to anywhere to money or time and ask for 22 samples, often you get kind of a negative look or a look of maybe just kind of disbelief or dismay or a blank stare. So the question would be then, how could we replicate this type of test? Maybe we could run longer, less samples, you know, that kind of thing. So let's just say, what if we run to 2 lives? So now this says hours here, just ignore that. The key is whatever our one life test is, that's 50,000 cycles we talked about, we're going to run one life here. Oh, we're not going to run, we're going to run 2 lives. We're going to run 2 lives and infer R90, C90 at 1 life. So we'll go run this again. This looks better. Now this says we could actually use 3 samples. So 3 samples, if we can get 3 samples to test 2 lives and not fail, based on this distribution, we can then infer R90, C90 at 1 life. Or, maybe we have kind of a trade-off here. We can say, let's run 1.5 lives and recalculate this. And now we're looking at 7 samples. So we can easily quantify where does this number of how many samples should I test actually come from. I've seen some very arcane methods to doing this. Maybe we test 3 samples and we average their lives together, and if that number is bigger than the design target, then we feel good. There's lots of different ways to approach this, but what I'm trying to show here is a good statistical manner in which we can look at statistics and previous failures and life distributions and concepts of reliability and confidence levels and all that, tie that all together. So we're not just saying, hey, ENCODE, what should my test specification be in terms of cycles and test time and that kind of thing, but also how do we tie that back together to an R90 and a C90, for example. Okay, so all that's available with ReliaSoft looking at the samples and test duration, and ENCODE looking at the fatigue-specific equivalent damage concepts. So with all that said, I hope that today we've met your our target here. We're going to be looking here at what is this whole tipping point here of the number of samples to test, how long to test for, because ultimately we cannot ignore the fact that our parts, we need to test and demonstrate some reliability metric, either a mean time to failure, mean time between failures, a characteristic life, or reliability and confidence, and so on. So I hope we've been successful in meeting that goal, tying together not just the durability, but also the reliability side of our test specifications. Thank you for your time, and I look forward to seeing you in future webinars. Thank you. Goodbye.